Alright, welcome back. Here is Chapter 9 lecture on planetary geology, Earth, and the other terrestrial worlds. So we know on the Earth we have volcanoes, and there are also volcanoes on other planetary bodies. Our goals in this section are going to learn about what terrestrial planets are like on the inside, what causes geological activity, and why do some planetary interiors create magnetic fields like the Earth does. So on the inside, Mercury is heavily cratered, long steep cliffs called scarps. Venus has a lot of clouds on it on the atmosphere, but has lots of volcanoes on the surface. Of course, Earth we know has craters and volcanoes, and the Earth's moon is geologically dead, had some craters and some volcanoes on it. And Mars has some extinct ancient volcanoes and drainage beds as well. Let's look at seismic waves, because seismic waves tells us a lot about an interior of a planetary body. The vibrations that travel through the Earth's interior tells us what Earth is like on the inside. And so we have several sections of the Earth's interior. The core is the highest density, it's in the middle, it's nickel and iron. The mantle is most of the inside of the Earth, it's moderately density, silicon and oxygen, the building blocks of rocks. And then the crust, the kind of the skin of the Earth, is the lowest density, that's made of granite basalt. So we can apply what we have learned about Earth's interior, which we did in Chapter 6 in Comparative Planetology, to other planets that tells us what their interiors are probably like. Now the Earth looks different on the inside in different layers because of something called differentiation. Gravity pulls high density material to the center. The lower density material rises to the surface, and the material ends up separated by density. In the lithosphere, the top layer of the Earth, a planet's outer layer of cool, rigid rock, that's the lithosphere. And it floats, quote, quote, on the warmer, softer rock that lies beneath a plastic, which is the mantle. So how do we know what's inside the Earth? We have two types of seismic earthquake waves called P waves and S waves. And they move in different waves. That's why we talked about them this way. P waves are pressure waves, and they can go through the Earth's core, but the S waves, the surface waves, cannot. And therefore we can conclude that the Earth's core must have a liquid outer layer. So what causes this geological activity in the first place? There are different processes, and these include accretion and differentiation when planets were young, and radioactive decay, which is the most important heat source today. Stuff on the inside of the Earth that is still decaying from radioactivity and heating up the interior. There are several ways this heat gets away from the interior outside. One is convection. This transports heat as a hot material rises and cool material falls, like a boiling pan of soup or rice. Conduction is in contact. It transfers heat from a hot material to a cool material. And then we have radiation, which is what sends energy into space. That's how we get energy from the sun, through radiation, electromagnetic waves. Size does play a matter here, and the smaller worlds cool off faster and harden early. The Moon and Mercury are now what we consider geologically dead. They don't have anything going on within them. So why do some planetary interiors create magnetic fields? Why does the Earth have one and some don't? The motions of charged particles are what create magnetic fields. A world can have a magnetic field if charged particles are moving inside of it. And there are three requirements: the molten, electrically charged interior, convection in the interior, and a moderately rapid rotation like the Earth has. So we have learned that all terrestrial worlds have a core, a mantle, and a crust. The denser material is found deeper inside. The interior heat drives geological activity on the outside, and radioactive decay is currently the main heat source. And planetary interiors that create a magnetic field require a motion of charged particles. Some of it has to be liquid inside of it. Now let's look at the surfaces of these planets. what processes shape the planetary surfaces, how do impact craters reveal a surface's geological age, and why do the terrestrial planets have different geological histories among the four of them: Earth, Venus, Mercury, and Mars. There are a number of features that can shape the surfaces. One is impact cratering, impacts by asteroids and comets. There's volcanism, the eruption of molten rock onto the surface. There's plate tectonics, the disruption of a planet's surface by internal stresses, the plates moving. And then there's erosion, surface changes made by wind, water, or ice. In impact cratering, most of the cratering happened soon after the solar system formed, 4.5 billion years ago. This does not play a big part today. The craters are about 10 times wider than the object that made them because of the velocity of the object. And small craters greatly outnumber the large ones because bigger objects are less in number than small objects. So on the left is a very famous crater, probably the most famous crater on the entire planet, something I have personally been to and seen. This is Meteor Crater, or also known as Barringer Meteor Crater in Arizona, outside of Winslow, Arizona, just east of Flagstaff. And on the right is the Tycho Crater on the Moon. And in the Tycho Crater, I think it's always neat to point this out, you see what we call a central peak. This is the splashback. When you throw a rock into a lake, you see a splash come up. This is the splashback of that molten material forming a rock on the Moon's surface. So we have ourselves a standard crater, a crater with a typical bowl surface. Let me get back to my PowerPoint here. Okay, hopefully that wasn't too much of a disruption. Impact into an icy ground, where you see ridges form, and then an eroded crater, where the crater shows evidence of erosion from wind, water, or ice. Volcanism. Volcanoes happens when a molten rock, magma, finds a path through the lithosphere to the surface. The molten rock is then called lava when it reaches the surface. So magma is underneath the surface and lava is on the surface. It's the same thing as melted rock. Volcanoes cause outgassing. This releases gas from the Earth's interior into the atmosphere, and it does change the atmosphere of the Earth. Then we have plate tectonics. The convection of the mantle creates stresses in the crust called tectonic forces. The compression of the crust creates mountain ridges that form upward, and the valley can form where crust is pulled apart. We see this in the Mid-Atlantic Ridge between North and South America and the European countries. So here are the plate tectonics on the Earth. The Earth's continents slide around on separate plates of crust, and we are on the North American plate. Parts of California are on a different plate called the Pacific Plate, which causes all the earthquakes out there. And then in the middle there, between the United States, South America, and Africa and Europe, we have the Mid-Atlantic Ridge, which is where the two plates are separating about 2 to 3 inches a year. We also have erosion. This is a blanket term for weather-driven processes that break down or transport rock. And these erosion processes can include glaciers, rivers, and wind. Here's the Colorado River and the Grand Canyon. I have come close to seeing the Grand Canyon a couple of times, but I've never been there, and I do hope I get to see it someday. I'm sure it's a beautiful sight. But it carves out the Grand Canyon due to erosion, and this has happened over many, many millions of years. By ice. The glaciers carved out in the Yosemite Valley are carved out by glaciers. By wind. Wind wears away rock and builds up sand dunes in the Sahara Desert. By erosional debris. Erosion can create new features such as deltas by depositing debris, and we have this in the New Orleans area in the Mississippi Delta. As the Mississippi River flows down the United States, it deposits sand and silt in this nutrient-rich area of the Mississippi Delta. So how do impact craters reveal a surface's geological age? Let's take a look at that. Most cratering happened in the first billion years. We don't see much cratering anymore. This is an early on thing because it swept up all the debris in the solar system. So a surface with many craters has not probably changed in about 3 billion years. Some areas of the moon are more heavily cratered than others, and younger regions are flooded by lava after most of the cratering has formed. So here's a map of the entire moon surface, and you can see the dark areas are lava plains, flat areas where lava has seeped through cracks in the moon surface to form lava flat plains, and then we have the craters in the highland regions. Well, the role of the planet's size plays a part in all this. The smaller worlds cool off faster and harden earlier. If you have a small bowl of soup, it's going to get colder faster than a big bowl of soup. Larger worlds remain warm inside, which promotes the volcanism and the plate tectonics. Larger worlds also have more erosion because the gravity retains an atmosphere to them, like Earth and Mars and Venus. The distance from the sun also plays a part. Planets close to the sun are too hot for rain, snow, ice, and so therefore they have less erosion, like Mercury and Venus. The hot planets have more difficulty retaining an atmosphere, like Mercury. Planets far from the sun are too cold for rain, limiting erosion, like Mars. And planets with liquid water, like the Earth, have the most erosion. So the Earth does have a lot of erosion. Rotation of the planet does play a part. Planets with slower rotation have a less weather effect, less erosion, and a weaker magnetic field. Remember, it takes motion inside the planet of a fluid metal to create a magnetic field. And the planets with a faster rotation have more weather, more erosion, and a stronger magnetic field, just like the Earth does. So we know that the processes that shape planetary surfaces include cratering, volcanism, tectonics, plate tectonics, and erosion. The impact craters reveal a surface geological age because the amount of cratering tells us how long ago a surface formed. And we know that differences arise because of the planetary size, difference from the sun, and the rotation rate. Now let's take a look at geologically active, the moon and Mercury. What geological processes shaped our moon and what processes shaped Mercury, which are now both geologically dead? So we mentioned the dark flat areas called lunar maria or lunar seas. These are smooth, dark lunar seas or maria. Maria is Latin for seas. They are less heavily cratered than the lunar highlands because the lava has filled in the craters. And the maria were flooded by the running lava. The early surface was covered with many craters, and then large impacts weakened the crust. Lava seeped up through the crust into cracks and filled in the low-lying areas. We know that wrinkles arise from cooling and the contraction of a lava flood. We do consider both Mercury and the moon geologically dead, quote, quote, because geological processes have virtually stopped. The moon does have moonquakes to them, but most of them are caused by impact features. What about Mercury? Here's a close-up of Mercury's surface. Mercury looks a lot like the moon does. Mercury is very close to the sun, so it's got a lot of cratering to it. And again, it also has low-lying features of lava and maria seas. There are these long cliffs on Mercury, called scarps, that shrank early in its history as the planet cooled, and left these large, mile-long cliffs. Okay, let's take a look at Mars now. What geological processes have shaped Mars, which is very different than Mercury and the Moon? And what does that tell us about water that may have once flowed on Mars, which we're still finding out about? Well, back in the day, 120 years ago, Percival Lowell misinterpreted surface features seen in the telescope images of Mars. He called them canali, and there was an Italian astronomer named Giovanni Schiaparelli who said these are canali. Canali meaning canals, and Percival Lowe in the United States said, well, canals are made by men. So the canals on Mars, the canali that Giovanni Schiaparelli talked about, must have been made by Martians. And this is really how the whole notion of Martians and aliens came to be, because of the canali, the canals on Mars. We know Mars has cratering. There's different cratering rates across the different Mars surface, and many of the early craters have been erased by volcanic features. Mars has the largest volcano in the solar system, Olympus Mons, or Mount Olympus. It is the size, wide ways, as the state of Arizona, or almost Texas. It's a very large volcano, and in fact Olympus Mons is 3 times the size of Mount Everest on the Earth. It's 90,000 feet tall and the size of the state of Arizona. Why is it so big? Well, you know, in Hawaii we have volcanoes, but the cause of those volcanoes is a hot spot on the surface of the Earth, forming lava and bringing it to the surface, but the plate, the Pacific plate, moves and spreads that lava out. Mars is geologically dead, and so that lava sits there and it keeps coming up into the same surface area and forms this gigantic volcano 3 times the size of Mount Olympus, Mount Everest on the Earth. We know there are a system of valleys, and the largest one is called Valles Marineris, known as Mariner Valley, discovered by the Mariner 9 spacecraft, thought to originate from Tectonics. Now, Mars is smaller than the Earth, but yet Mars has the largest volcano in the solar system, and this Valles Marineris is a channel, kind of like you can think of it as the Grand Canyon, except a Grand Canyon that stretches from California to New York City. This canyon is 3,000 miles long and at some points 10 times as deep as the Grand Canyon is in Arizona. Quite a remarkable feature. Well, there are evidence of features that show us that water once flowed on Mars. There are dry riverbeds. Close-up photos of Mars from our spacecraft have shown what appear to be dried-up riverbeds. The details of some of the craters on Mars suggest that they were once filled with water and have now eroded and evaporated. The rocks on Mars have shown us from the Mars rovers Spirit and Opportunity and Curiosity that rocks appear to have been formed in water, standing water. These little blue things you see on the picture here we call them blueberries. We like to name things kind of oddly in NASA science. These are called blueberries, and we have found these rocks to have formed in water. I can't think of the scientific name of the blueberries right now. We just call them blueberries because they look like round blueberries. But they were formed in water. We can map the hydrogen content in blue here on the surface of Mars. Shows that low-lying areas contain more water ice. And so there are 2 ice caps on Mars. The North Pole ice cap is carbon dioxide, or dry ice, and the one on the South Pole is a water ice cap. We see gullies on Mars, inside of craters, probably formed from underground water canals that seep through the canals and go through the crater walls and then flow debris down into the crater surface. So these gullies on crater walls suggest occasional liquid water has flowed, and has happened less than 1 million years ago. So this is very recent in planetary history. So we have learned that there are differences in cratering across the surface, that giant shield volcanoes exist, and that evidence of tectonic activity exists on Mars. We know that some surface features look like dry riverbeds. Some craters appear to be eroded by wind and water. Our numerous rovers on Mars, which my former intern is in charge of landing. I have a former intern who works at NASA. She was my high school intern many years ago, and her job is to land rovers on Mars. And these rovers have found rocks that appear to have formed in water. And then there are gullies in the crater walls that may indicate recent water flows. So let's now switch away from Mars and go to Venus. What geological processes have shaped Venus? And does Venus have plate tectonics? You know, Venus has this big thick layer of atmosphere to it. 90 times thicker carbon dioxide than what we see on the Earth. And so we have not, the United States has not landed a spacecraft on Venus because Venus is at 900 degrees Fahrenheit. It would melt. The Russians have landed 2 spacecraft on Venus called Venera 1 and 2. They melted pretty quickly on impact, but they did capture a picture or two just for prosperity reasons. But we do see these processes on Venus. So instead of landing a spacecraft on Venus, and we know it's covered by thick clouds, we use radar mapping to see the surface. And so its thick atmosphere on Venus focuses us to explore Venus's surface through radar mapping. We know that Venus has impact craters, but fewer than the Moon, Mercury, and Mars. And let's think about this for a minute. Why would Venus have fewer craters than Mercury, Mars, or the Moon? Those objects don't have an atmosphere. And the atmosphere of Venus burns up most of the stuff that's going to hit it before it ever hits the surface. It does have many volcanoes, including both shield volcanoes and stratovolcanoes. And we call these volcanoes in the lower right picture here pancake volcanoes because the surface pressure on Venus is so thick, the atmosphere is so high pressure that it doesn't allow for volcanoes to spew lava out into the atmosphere. They just kind of float down and make these pancake domes. Pretty neat stuff. We know the planet's fractured and contoured surface indicates tectonic stresses have formed in the past. Here's a picture from the Russian spacecraft Venera 1. The rocks shown little erosion to them because of the atmosphere. So we know that Venus does not appear to have plate tectonics, but the entire surface seems to have been completely resurfaced and repaved in the last 750 million years ago. Maybe because of the lithosphere changing or some weaker convection in the surface. So we know that Venus does have cratering, volcanism, and tectonics, but not much erosion because of that thick atmosphere. The lack of plate tectonics on Venus is a mystery to us at this time. And so now we go from Mars to Venus and the Moon, now to Earth. Why is the Earth's surface shaped by plate tectonics? And was Earth's geology destined from birth? So here again is the plates on the surface of the Earth. We have seen this before. We are on the North American plate with the Mid-Atlantic ridge between us and Europe and Africa. We know that the motions of the continents can be measured with GPS measurements. They do move several inches a year. The idea of continental drift was inspired by a puzzle-like fit of the continents. You can see here where South America seems to fit in right in the notch of Africa, and the mantle material erupts where the seafloor spreads. A thin seafloor crust differs from thick continental crust, and the dating of the seafloor with radiometric dating shows that it's usually quite young, pretty new material in the seafloor. And so because of these convection cells inside the mantle and the Mid-Atlantic ridge, we see that seafloors are recycled through a process known as subduction. The material is subducted down beneath the surface and recycled into the mantle as new rock. There are major geological features in North America that record the history of plate tectonics. For instance, we have the Himalayas, formed by a collision between 2 plates in Asia. The Red Sea has formed where plates are pulling apart. The San Andreas Fault in California is a plate boundary. It's a subduction zone. It is a transform fault, not a subduction zone, but a transform fault where 2 plates are sliding past each other, and so San Francisco and Los Angeles are actually coming closer together to each other because of this. And this can cause earthquakes. We haven't had a really big earthquake in California since about the late early 90s. We had the earthquake in California that was pretty bad. We can tell that the measurements and plate motions tell us the past and future layout of the continents. And then we mentioned in the last chapter about the hot spots over Hawaii. So there's a molten hotspot of lava under Hawaii, but the Pacific plate moves on top of that and spreads out the islands over a spread area. But the hotspot remains and keeps flowing lava up into it. So many of the Earth's features are determined by the size, the rotation, and the distance from the Sun. And the reason for plate tectonics is not yet clear. It's one of the biggest mysteries in planetary geology. So we have learned that the measurement of plate motions confirm the idea of continental drift, and plate tectonics is responsible for both subduction, seafloor spreading, mountains, rifts, and earthquakes. Many of Earth's features are determined by its size, distance from the Sun, and rotation rate, and the reason for plate tectonics is yet still a mystery to us. We don't know. We're dying to find out.